For more physics-related videos, please subscribe. Welcome to the Physics Almanac. This video is going to cover projectile motion and specifically problems involving maximum height. I've rated the physics level in this video as easiest. In a previous video, I derived the three kinematics equations for projectile motion. These three equations are the only equations necessary to solve every single projectile motion problem you'll ever encounter. Now in that video, I also covered a fourth useful but not necessary equation. This equation relates the y velocity to the y position and comes from simply combining the y position and the y velocity equations as functions of time. You don't need this equation, but it can be useful and save you a step if you get problems that don't involve time. Now for this video, we're asking specifically about maximum height problems. Projectiles, while traveling through the air, will trace out a parabolic curve before landing. The maximum height is when the ball is at the apex of this parabola. So what's special about this point apart from being the maximum height? Well, if we take a look at the velocity, velocity is a vector that points tangentially or parallel to this parabola at that point. In general, it will have a y component and an x component. However, at the maximum height, this vector, which points tangential to the curve, is going to point entirely in the x direction, meaning there is no y velocity. This should make sense because this is the point where vertically the ball is turning around. Prior to reaching the maximum height, it's going up. Afterwards, it's falling back down. So that is what you should recognize every time you get a maximum height problem. The y velocity is 0, or equivalently, the velocity is equal to the x velocity. Because this is the apex of the parabola, this is the only point in that parabola where that y position is going to be reached only once. Everywhere else on the curve, you will get two solutions for that y position. You'll get a solution on the way up and a solution on the way down. As a result, maximum height problems are the easiest projectile motion problems. So let's do an example. In this example, a golfer hits a ball off a cliff of height 25 meters with an initial speed of 180 kilometers per hour at an angle of 10 degrees above the horizontal. What are the ball's horizontal position and vertical position above the ground, which is the base of the cliff, when it reaches its maximum height? In a previous video, I covered 5 steps to easily solve every projectile motion problem. So let's follow those steps for this question. Step 1, draw it. This will help you visualize what's going on, allowing you to get some sort of idea of what type of answer you're expecting, and when you get to the end, you can check to see if your answer makes sense. So for this problem, we have the ground and a cliff of height, which I'm going to call y0 above the ground. The golfer hits a ball off this cliff with an initial velocity of v0 in a direction at an angle theta above the horizontal. The ball is going to trace out a parabolic path until it hits the ground. Theta, by the way, in principle could be negative, which means you'd be hitting the ball downwards instead of upwards. Now for this problem, we care about the point when the ball reaches its maximum height, which I'm going to call h, as measured above the ground, not the cliff. At that point, the ball will also have an x position, which I'm going to call delta x. This is the distance it traveled in the horizontal direction. Step 2 is to write down everything you know and don't know. Remembering that, for projectile motion problems, there are a total of 5 variables: the x position, the y position, the x velocity, the y velocity, and time. And notice that all of these quantities change with time, except for the x velocity, which is constant. Now, what information are we given here? We're given the initial velocity, which is a speed of 180 kilometers per hour at an angle of 10 degrees above the horizontal. We're also given the height of the cliff, which is 25 meters. What we don't know is the time at which we reach the maximum height, what that maximum height is above the ground, and what the x position at that point is. Now remember that velocity is a vector, so the initial velocity is also a vector, so it's going to have an x component and a y component. Since we're given this angle above the horizontal, theta, we know that the x velocity will be v0 cosine theta, and the initial y velocity will be v0 sine theta. Now notice that I wrote Vx and V0y. I did not write V0x. That's because the x velocity is constant. So the initial x velocity is the same as the x velocity at any other time. Whereas the y velocity does depend on time, so you need to specify that this is only the initial y velocity. During this step, it's good to ask yourself, is this a when question or a where question? Does this question involve time or does it involve location? In this case, this is a where question. We're being asked about the horizontal and vertical positions. Don't be fooled just because the word when is in the question. This is just an unfortunate linguistic happenstance. This when does not refer to time. It refers to a point along this trajectory, specifically the point of maximum height. If this were a when question, we would either be asked about time or be given information about time. The last thing you should do during this step is make sure you define where you're going to set your height equal to 0. Where is y equals 0? Now, most of the time, the most convenient and reasonable location to place your y equals 0 is on the ground, and that's what I'm going to do in this problem. However, this is one of those problems where it would be equally reasonable to place y equals 0 at the top of the cliff, in which case the ground would have a position of negative y naught, negative 25 meters. If this video is helping you out so far, I just ask that you like and subscribe, maybe share it with some friends and classmates. Step 3 is to make sure you know what is being asked. And does this problem involve one of the special points? Special points being the initial position, the highest point, or the landing point. Well, what's being asked in this problem is the positions, both x and y, when you reach the highest point. So yes, this is a special point problem. Specifically, it's a highest point problem. And what characterizes highest point problems? The y velocity is 0. This should be automatic. Anytime you see a problem involving the highest point, you should immediately go Vy equals 0. Step 4 is to make sure you separate your horizontal and vertical equations of motion. We have 3 kinematics equations. One of them refers to the x motion, and 2 of them refer to the y motion. So make sure when you solve this, you don't use the x equation for y motion and vice versa. You will get the wrong answer if you do this. Now, because this problem involves Vy equals 0 and we're being asked about position, meaning it's a where question, not a when question, it might be useful to make use of this optional blue equation, which doesn't involve time. However, in this case, we're also being asked about the x position, and to find that, you have to find time. So making use of this blue equation is not going to save you any steps. So now that we've summarized what we know and what we're looking for, we can proceed to solving this problem. First step, this is a highest point problem. Y velocity is 0, so we can take our y velocity equation and set it equal to 0. We can solve this equation for time to get that is v naught y over g. At this point, you might be tempted to say, well, I know v naught y, it's just the acceleration due to gravity, so let me plug in some numbers to get that time equals 3. Don't do this. Remember the 5th rule. Solve your equations without plugging numbers until the very last step. You don't want to plug in any numbers until you get an equation of the form, the thing I want equals a bunch of stuff I already know. In this case, the thing I want is not time. This question's not asking about time, it's asking about position. So we haven't reached that point. The only exception to this rule is if you know that a quantity is 0. In that case, plug it in right away, it will simplify your equations greatly. And that's exactly what we did here. We knew Vy was 0, so first thing we did was we plugged that in. Why don't you want to plug in your numbers right away? There's a number of reasons for this. The first reason is, notice here, I didn't specify any units. If you're plugging in your numbers at every step, chances are you're not going to carry your units through every single step. That's going to be tedious, you're going to get lazy, and you'll just omit the units. So when you get to the end, you won't know if your units make sense. And in fact, if you take a look at this example, I have a problem with my units, because the velocity that was given was in kilometers per hour, but g is in meters per second. So whatever my units of time is, it's not going to be seconds. In fact, in this case, the units will work out to kilometers times seconds squared per meters hours. What you need to do here is make sure all your units are consistent and convert your initial velocity to meters per second instead of kilometers per hour. And when you do that, you get an initial velocity of 50 meters per second. So that's the first problem. You're increasing the chances of making a units error. Furthermore, if you realize your answer doesn't make sense and that you made a mistake somewhere, there's no way to find out which step that mistake was, and you're going to have to start the problem from the beginning. Whereas if you had solved this with variables and not plugged in your numbers, you would be able to track every single algebraic step, so you'd be able to see if your algebra was correct. And you'd be able to find any mistakes you made. So if you knew you made a mistake somewhere, you wouldn't have to go all the way back to the beginning of the problem. You just have to go back to the step where you made that mistake. And you won't have to worry about carrying through units. You're only going to plug in your numbers and units at the very last step. A final reason you don't want to plug in your numbers now is that if you plug these numbers into a calculator, you don't get exactly 3. I rounded this off. And if you're plugging in numbers at every step, you're almost certainly going to end up rounding off at every step. So even if you get your units right and you do all your algebra correctly, if there are a lot of steps and you've rounded off at every step by plugging in your numbers, it's likely you're still going to get the answer wrong even though you did everything correct. So by only plugging in at the last step, you're guaranteeing that you're only going to round off once. So don't plug in your numbers at this stage. Starting with the x equation, we just have to plug in our expression for time into time in the x equation. Now, since this involves Vx and V0y, and we already know what that is, we know that V0y is V0 sine theta and Vx is V0 cosine theta, we can substitute that in as well. So we're going to get that delta x equals V0 cosine theta times V0 sine theta over g. Now we have an equation of the form, the thing we want equals a bunch of stuff we know. We can plug in our numbers. Before I do that, notice that we have a V0 here multiplied by a V0 here. So this whole thing is actually going to have a V0 squared. So plugging in our numbers, making sure that our units are consistent, we get that the x position at the point where the ball reaches its maximum height is 44 meters. Now that we found the x position, we have to find the y position. But be careful, we're being asked the height above the ground. This equation is for delta y, the change in y. So the total height above the ground when the ball has reached its maximum height will be the change in height plus the initial height. Well, the ball started at the top of the cliff, so the initial height is y0. So don't write down h equals delta y, that'll give you the height above the cliff. We want the height above the ground, or the base of the cliff. Again, we play the same game. We plug in our equation for t into our expression for delta y. And this expression is a little more complicated, but it can be simplified. This second term here, we have V0 sine theta times V0 sine theta divided by g. So that's going to be V0 sine theta quantity squared all over g. In this last term, we have a V0 sine theta squared here. Then we have a g divided by g squared, which is 1 over g. So these two terms are actually like terms, but this has a factor of +1 and this has a factor of -1/2. So we get that h equals y0 plus V0 sine theta quantity squared all over 2g. And again, we now have an expression of the form, the thing we want, h, equals a bunch of stuff we already know. So we can plug in our numbers to find that the maximum height above the ground, the base of the cliff, is 29 meters. And that's it. Easy peasy lemon squeezy. In the next video, we're going to be taking a look at projectile motion problems involving the landing point, or range. So if you found this video helpful and think you'd like some help on solving range problems, please be sure to like and subscribe, and hit the bell to be notified for the release of this video, as well as other physics videos in general. Thanks for watching, and I'll see you in the next one.